something falls near the Earth's surface, it accelerates and the acceleration is constant. Its velocity isn't constant, its velocity is changing, but its velocity is changing at a constant rate. Now, this is in the absence of air resistance. Because we're doing high school physics here, so we like to disregard things like friction due to air. We'll see what that could mean later. So we call this free fall acceleration, and it is abbreviated with g, lowercase g, not a capital G, lowercase g. So g is equal to 9.81 meters per second squared. That's the commonly accepted number. If we were Fermi estimating, oh my, yeah, I got problems. If we were performing a Fermi estimate with acceleration due to gravity, we would just say 10 to the first. Roughly 10 meters per second squared is what you're going to pick up. G is towards the center of the Earth. The acceleration is downwards towards the center of the Earth. So by convention, we have always shown down as a negative because we have that, ridiculous Cartesian coordinate system that we like to superimpose on the entire world because we can. Descartes was really an evil, evil human being, aside from his contributions to math. Well, evil in present context. Anyway, I can't get past it. We typically show this acceleration as negative g, which is negative 9.81 meters per second squared. Okay. So, what goes up? When the only force working on something, when the only force that is causing acceleration is gravity, your acceleration is 9.81 meters per second squared down. End of story. So this is where we get to throw things up. Throwing up and falling down, you've been doing it. As this ball rises, and I'm going to not really throw it up, I'm going to pretend to throw it. As it rises, is its velocity changing? Yes. Its velocity is in a positive direction, and its velocity is approaching zero. It starts with high velocity. I'm going to break something if I do that again. Eventually, its velocity reaches what? At the top, 0. And then its velocity starts to increase in magnitude in the negative direction. Acceleration as it rises, 9.81 meters per second squared, down. Acceleration at the moment when its velocity is 0 and it is stopped at the top and it prepares to start falling, still 9.81 meters per second squared, down. Its acceleration as it falls, you guessed it, 9.81 meters per second squared, down. And this is just because I like to, what can't be beat? A dead horse! But I'll try anyway. In free fall, there's only one acceleration, and it is 9.81 meters per second squared, down. Now, this person is actually probably not completely, this insane person, accelerating at 9.81 meters per second down, squared, down. Why?
Air resistance.
Air resistance. They're spread out. And if they were to do this, they would immediately see that 9.81 meters per second squared downward. We typically do scenarios where we can disregard air resistance. The ball accelerating at, as it's being thrown up, 9.81 meters per second squared. If they jumped off the top of their water dish, they would accelerate at 9.81 meters per second squared downward. Here's where we are going to talk a little bit about the tricky bit, and this is the Cartesian coordinate system, René Descartes. Sign we use as a proxy for direction. So you know that a vector quantity has to have a direction attached to it. We can't just say something is traveling at 40 meters per second. We can't just say that it's accelerating at 9.81 meters per second squared. We have to indicate direction. So we can say 9.81 meters per second squared down, or we can use sign as a proxy. And again, because we tend to impose this Cartesian system on the world, we call up positive, down negative. Easy enough. Upwardly thrown objects, we would therefore say have decreasing positive velocity, while falling objects have increasing negative velocity. Not so hard, we just got to keep track of it. I should be more careful with my autocorrect capitalization. So G has a magnitude of 9.81 meters per second squared. It's generally used as a negative. So we generally talk about negative g. Your book does a whole thing that it's one of the very few arguments I have with your textbook. I think it's a good layout for physics in general. They take all of your stuff like VF equals VI plus A delta T, and they say, well, if you're applying this to free fall on the y-axis, then it's VF equals VI plus negative G delta T. I prefer to just recognize that my acceleration on the y-axis is going to be negative 9.81 meters per second squared and plug it in that way. So again, your book does this to get you used to the using G as a variable. I traditionally have not. And we'll use G as a variable when we get the force problems because you'll have mg, F sub G equals mg. But for now, I'll continue to use acceleration, and I will sometimes note, acceleration, grav, and anyway, that's what I do. Like I said, I'm a biologist masquerading as a physics teacher. So let's do the sample problem on 64, and then I'll cut you loose. Let's talk about we'll do the sample problem, I'll cut you loose, and then tomorrow we're going to come in, and I'm going to introduce one thing after you've had a little bit of practice. So we have some co-ed volleyball, and Jason hits a volleyball so that it moves with an initial velocity of 6.0 meters per second straight up. If the volleyball starts from 2 meters above the floor, how long will it be in the air before it strikes the floor? Assume that Jason is the last player to touch the ball. So this is where drawing a picture is enormously helpful. So I'm going to draw my ground, which is 0. I should make clear that that's a 0. This is my 2 meters above the ground, and this is where my volleyball starts, and I can't draw a volleyball to save my life. This probably looks like a soccer ball. I don't care. So I've got a ball that's starting at 2 meters above the ground. It has an initial velocity here of 6.0 meters per second, and that's positive 6.0 meters per second. And what I want to know is delta T until it hits the ground. Can this be done? Yes, of course it can. So there are 2 ways to do this, and this is where we'll talk a little bit about 6 ways to solve a problem. 5 of them get you an answer, 3 of them get you a right answer, and 1 of them is elegant. Let's set up all of our known variables. VI, positive 6.0 meters per second. What's the acceleration of the ball through the entire thing? Acceleration is equal to negative g, which is equal to negative 9.81 meters per second squared. Do we know final velocity? Be very careful here because people want to say 0, and it's not 0. Does it stop before it slams into the gym floor? No. It's continuing to accelerate. If we pulled the gym floor out, it would keep going until it hit the center of the earth. So hitting something doesn't make the final velocity 0, but that's a really common error. So we want delta T. Do we have its displacement? Do we have its delta Y? So let's review the difference between displacement and distance. The distance it travels is this. Its displacement is the difference in its starting position and ending position. What's its displacement? Negative 2. Yes, it's 2 meters, but it's 2 meters in the negative direction. So delta Y equals negative 2.0 meters. And delta T is of course what we want. So do we have a single equation that ties together these things? And here's where I wait for somebody to go, we don't have any equations with delta Y. It's the same exact equations, we just use delta Y instead of delta X. In the next chapter, we'll merge those, and we'll have equations that deal with both delta Y and delta X, and it'll be an unholy marriage, and it'll be all kinds of fun. But for now, just enjoy one axis. So we've got a couple of options here. We have delta y equals vi delta t plus 1/2 a delta t squared. Is there a problem with that? Well, delta t is what we want, but that equation ties together the 4 elements that we have. Oh, so what's the problem with that? How would it be hard? Explain it. Give me words. Use your words. We would have to use it's the dread enemy, if you're me. Quadratic! Yeah, we would have to use the quadratic equation. You knew that. So if you're willing to use the quadratic equation, you can do this. The problem often comes in with getting it rearranged in such a fashion, and you can absolutely, certainly, if you are a quadratic equation nut and you just do the quadratic equation for fun in your spare time, recreationally, at home, knock yourself out, sweetheart. I will go to tremendous lengths to avoid the quadratic equation. So that would be the simple, elegant solution. Let's look at the slightly clunkier solution, which is actually what I think your book recommends. Okay, so let's talk about some things we know. What if we treat this travel of this object as 2 segments? Segment 1 and segment 2. That's what you were thinking. Awesome.
Like up and
yeah,
then
up
down.
and down. So we have segment 1 of travel. And segment 1 of travel has a VI of positive 6.0 meters per second, has an acceleration of negative g, or I could shrink that, I guess, negative 9.81 meters per second squared. Do we know delta y? We don't know how high this thing goes. Do we know anything else about that first segment of travel?
Velocity final.
What's the velocity final? 0. Yeah, guess when it stops and turns around? When the velocity reaches 0. It's fun doing physics in funny voices.
This is what I was thinking, and then you started doing more stuff, and I was like, I guess that was wrong.
Nope, not at all. So I'm gonna note that that's VI1, VF1. Because that's for segment 1, if we're doing this in segments. Now, what's the other thing that we're looking for, really? Delta T. Do we have an equation that ties together VIA, VF, and delta T? By golly, we do. Would we agree that VF plus VI, VF equals VI plus A delta T would work here? Of course we would. You're all reasonable people. And furthermore, you're all, algebra using primates, so we would all also agree that VF minus VI divided by A equals delta T. Okay, so we can find the time it takes this thing to get the top of, I very often call this position top of flight, because that's what it is. Top of flight is the point at which, velocity on the y-axis equals 0, and objects begin to fall back towards Earth. So we've got an equation for that, and this would be, and I'm going to note here, up. Now, I'm going to tell you the classic mistake that people make with this kind of problem on tests is they do this and they go, I'm done. Are you done? Of course you're not done. The other classic mistake is that they go, oh, okay, well, it took that long to go up, it'll take that long to go down. Is it going the same distance down? No. Oh. Okay. So, and I'll switch colors yet again. So for segment 2, which is this part of the travel, do we have a VI?
Yes.
Yes, what is it?
6 meters
Is it?
0.
0. The final velocity on the first segment is the initial velocity on the second segment. So VI part 2 is 0 meters per second. Do we know the final velocity? Nope. I have no idea how fast that thing's going when it slams into the gym floor mercilessly. Don't care, actually. Do we know how far it falls? No, we don't. Do we know its acceleration?
Yes.
Yes. So we know its acceleration is negative g, negative 9.81 meters per second squared. We want delta t. Do we have enough information here? Nope. So we have to get one of two things. We have to get the distance that it's falling, or we have to get its final velocity. So its final velocity is dependent on the amount of time that it has to accelerate, and we don't know that. The distance that it falls, however, is dependent on its motion in segment 1. So we're going to go back to segment 1 and figure out how far up this thing goes. This is not elegant. This is not, beautiful and clean. And then I'll show you a dirty little trick at the very end. So if we want, in fact, if we want to get delta y, because we don't know that, well, delta y would equal, so delta y2 would equal delta y1 plus what? How much further did it fall than it rose? 2 meters. 2.0 meters. And just in the interest of good bookkeeping, I've made a note up there at the top that delta t total, since I'm going around the barn on this and I'm not using the quadratic, delta t total is equal to the time up plus the time down. So if I want the distance up, so if I want delta y up, well, let's see. I have VI, VF, and acceleration. Is there anything that links those three to delta y? Do I have an equation? Get your card out. So we got VF squared equals VI squared plus 2a delta y. We know we have one nice thing being we can go ahead and rearrange for that. So VF squared minus VI squared divided by 2a equals delta y. We know that that goes away because VF is 0. So negative VI squared over 2a will tell us how far the object rises into the air before it stops. Maximum y position.